Hello, students. Yes, I am here at work. Yes, you do have a little video assignment. You just need to watch this video just to keep us on track. I know, we all want to just relax, but unfortunately, I have a lot of interesting stuff I'd like to cover, and I have a feeling if I put off too much of this, we're not going to get there, so I'll just go a little bit into the chapter, a little bit more to the chapter. So here we go. We had left off looking at the ClOx cycle, the big catalysis by HO radicals and H radicals. Well, we also have NOx, NOx, which mean NO and NO2 largely. They're collectively referred to as NOx, and these guys are largely produced through combustion. We talked about this when we in the first chapter. We talked about this gets produced in the engine, but this also gets produced by power plants and other heating things. So NO and NO2 can be generated through combustion with N2 and O2. Now, these radicals are typically very short-lived, 4 days, and they're usually converted to nitric acid that will fall out as acid rain, which we'll talk more about in Chapter 5. So very little of the NOx produced in the troposphere makes it to the stratosphere, but that doesn't mean none of it does. In fact, in the 1960s, there was a fear of increased ozone destruction through the use of supersonic aircraft that were capable of flying in the stratosphere, because they would be dumping all their pollutants out of the engines into there. Such commercial flights have since been disbanded, so any contribution that from our fears is thought to have been minimal. But there are similar worries of booster rockets and the space shuttles producing HCl during the launch. While currently this contribution to ozone depletion is minimal, people are looking at alternative rocket propulsions so that we aren't potentially producing catalytic ozone depletion chemicals. But in reality, the principal source of NOx is not from NO or NO2, but it comes from nitrous oxide, which is our dinitrogen monoxide molecule. Nitrous oxide can be formed in a process of the denitrification of the soil under certain reducing conditions. So reducing be like swamps, for example, swamp gases. When you have low amounts of oxygen, you can have reducing conditions. So while this process is a natural process, it does depend on certain concentrations of nitrogen in the soil. So this can be augmented by overuse of nitrogen fertilizers or fertilizer runoff. But this has caused a slow yet steady increase in nitrous oxide from 275 ppbv in the pre-industrial era to something like 319 in 2007, with an average increase of about 0.6 parts per billion by volume per year. So, nitrous oxide does not absorb visible light, and it does not dissolve in water. So its residence time in the troposphere is like 120 years. So because it doesn't absorb light, so it doesn't fragment in the visible spectra, and because the not dissolving in water means it doesn't get washed out when it rains. And so much of this can migrate into the stratosphere, where the following reactions can then occur. So on along, dinitrogen monoxide gets hit by light. It splits into N2 and a monooxygen, which isn't necessarily bad right away. But N2O, if instead gets hit by an excited oxygen, which remember forms in the presence of in the ozone destruction by UV light, it's a natural process. It will break apart into two molecules of NO, two radicals of NO. So at altitudes greater than 30 kilometers, the dinitrogen itself can photolyze to form ground state mononitrogen and excited state mononitrogen, so an excited and a ground state. So look, the N2, if we dump a bunch of the N2 at high enough atmospheres, get the excited process. So I'm just showing you what the electronic state looks like. The ground state one, remember, would have a completely set of unpaired electrons in the p orbital. But the D2, the excited state, would cause one of the electrons to spin, flip, and pair up. So that's a situation of the excited and ground state. Now the ground state nitrogen can react with oxygen that is already present there to form an NO radical and monooxygen. And once this NO forms, the catalytic cycle can occur. So NO reacts with ozone to form NO2, and then NO2 reacts with monooxygen to regenerate it. Of course, that monooxygen could be coming from the N plus O2. It could come from the N2O being cleaved. All the types of monooxygen can happen. However, other reactions can occur, such as reactions with hydroxyl radical to form nitrous acid, which isn't a catalyst and it doesn't react. So in fact, you don't see, if you have a bunch of hydroxyl radical and a bunch of NOx radicals, you don't see a dramatic increase in catalytic ozone decomposition. They actually fight each other. So once OH radical and NO radical bump into each other, they form nitrous acid, that can then leave the stratosphere and go back down and rain out as an acid rain. Now, the final major catalyst is ClOx and Brox, the chlorine monoxide radicals, or chlorine radicals and bromine radicals. They are the most reactive catalysts for ozone decomposition. They derive from natural and anthropogenic sources, so we cannot permanently remove them, but we can lower their amounts. The major natural source is through methyl chloride, and this can be produced largely in biological ocean reactions and sometimes through burning of vegetation and even by volcanic emissions. So coming out of volcanoes, wildfires, and reactions that occur within the ocean. Now, the majority of it is itself destroyed before it reaches the stratosphere, so it has a lifetime of 1 year. Less reactive than, say, NO, but far more reactive than N2O. So, methyl chloride can, for example, react with OH radicals to form a radical methyl chloride and water. And that once you kind of form the radicals, if they form that in the troposphere, they're going to react and completely decompose before it gets there. Other sources can be, for example, hydrochloric acid, which can form in the volcanoes, and just forms that come from chloride from the sea spray. But those are very short-lived, and they tend to wash out in rainfall. So both of those are soluble in the water. But when this methyl chloride reaches the stratosphere, the light, instead of cleaving the hydrogen, cleaves the chlorine off of there. And that chlorine radical can then initiate our catalysis. Just like the other guys, chlorine takes an oxygen from ozone and then reforms itself when it reacts with a monooxygen. However, other reactions can occur that can be far more reactive, as they can bypass the need of the monooxygen. The second step is often the slow step because the concentration of monooxygen is very low. So if you can find a way to get around that second slow step and regenerate our catalyst, we can destroy a lot more ozone. So for example, if you have the HOO radical, you can form HOCl. And that HOCl, the hypochlorous acid, can then be cleaved back into the OH and a chlorine radical. So we essentially took the step 2 ClOx and the step 2 HOX and turned them both into step 1. So crap. And then that chlorine radical can react, and the OH radical can react. So essentially, it speeds up and you get 2 ozones decomposing to 3 oxygens. BRO, so BRO radical and ClO radical can both react to form bromine, chlorine, and oxygen. And then the chlorine and bromine can then go on to react. So the idea being some of these step 2 radicals can react to regenerate their step 1 intermediates. While these mechanisms cover about 60% of the decomposition of ozone by halogens, the major source of chlorines is not coming from this methyl chloride, but actually from CFCs. What is a CFC? A CFC is a chlorofluorocarbon. Now, these were originally developed in the 1930s. We've since discontinued them from the 1990s, but the legacy is still ongoing. The idea is this chemical has a very low viscosity. So, it doesn't pour quickly. It's very sludgy. Has a low surface tension. Has a very low boiling point. And it's chemically and biologically inert. It was very, very useful. Very, very useful. It was non-toxic. It's non-flammable. It's great for all these uses where we're like, oh, hey, we don't want to be poisoned. This spills out. It's not going to just kill everyone around. And so we used it for all these various, very useful things. Like we can easily compress it to a liquid. It makes it very easy to store. And then when we allow it to expand and then boil and extract large amounts of heat, it was useful, and among other things, in refrigerants. Because the refrigerator, essentially, we compress to a liquid, then expand and absorb heat, and absorbs the heat, and that pulls the heat out of the fridge, and then we pump that heat out the back as we compress it again. It was used as a blowing agent. So you want to make a polymer foam, and you may want to make it fluffy. Well, we didn't want to use oxygen or water. We blew it with this gas, and it was used as a solvent. Now, the CFCs all have numbers associated with them. The numbering system itself was defined by, you have the number of carbons, the number of fluorines, and the number of hydrogens. And then the number of chlorines would make up the rest, because every molecule has, for every one carbon, will have 2 times the number of carbons plus 2 hydrogens or halogens. So like if you have 1 carbon, it should have 4 hydrogens or halogens. If it has 2 carbons, it should have 6. 3 should have 8. 4 should have 10, you're basically doubling the number of hydrogens and then adding 2. So a CFC would give it a number X, Y, Z. That you take the number of carbons minus 1. So it's left off if your X is 0. So like if you have 1 carbon, it's only going to be a 2-digit number. But if like 5 carbons, it would be an X of 4. The number of hydrogens plus 1 is Y, and Z is the number of fluorines. So like for example, if you had 1 fluorine and 3 hydrogens, you would have, and on 1 carbon, it would be 41. That would be your CFC. If you had, and that would be no chlorines. If it was 31, it would be 1 carbon, 2 hydrogens, a fluorine, and a chlorine. So here's some examples, CFCs. CFC 11, 1 carbon, 0 hydrogens, so that's why it's 11, why the second digit is 1, and 1 fluorine. CFC 12 is 2 fluorines. 113, that's a 2-carbon system with 0 hydrogens. CFC 114b is an isomer, and 115. But so different isomers, which isomer is when we have a different attachment of molecules. Often they get an A or B addend to it. So to get the formula, you can easily just add 90 onto the number. So, for example, CFC 11, if you add 90, you'd get 101, which is the number of 1 carbon, 0 hydrogens, 1 fluorine, and then chlorine is whatever's missing. But if we look at this, so tropospheric lifetimes, 45 years, 100 years, 85 years, 300 years, 1700 years. Well, CFCs are heavier than air. Troposphere has a lot of convective mixing, so they could easily reach the stratosphere, blown up there. And because they're chemically inert, they don't decompose until they're struck by high-intensity ultraviolet light. And you don't get that in the troposphere. So they don't break down in the troposphere. They only break down when they get to the stratosphere. When they get the light, they get cleaved off and we lose the chlorine. So you can see the release rate in 1988 versus the release rate in 2005, and see how they've slowly been decreasing they peaked in 1990 and how they've slowly been decreasing since then, to some extent. So ODP is the ozone depletion potential, how damaging they can be to the ozone. So 115, while has a long lifetime, doesn't do as much damage to the ozone. Now, as I said, the destructive potential is measured compared to CFC 11 based on reactivity, atmospheric lifetime, and the molar mass. Now, the Montreal Protocol. Keeping going with this. So the Montreal Protocol was something we developed in order to, when we recognized the problem. It's the Montreal Protocol of Substances that Deplete the Ozone Layer is a landmark international agreement about CFCs that was signed in 1987. So in the 1960s, it was first suggested that humans were damaging the ozone layer. And it wasn't until 1974 where we first had the first substantial hypothesis that, CFCs are highly damaging to the ozone layer. We had this guy developed by a scientist, and then this would lead to the Vienna Convention for the Protection of the Ozone Layer in 1985, which would lay the groundwork for this Montreal Protocol. It was the first major international agreement set to try to curb this damage, curb the climate change in general. The protocol was signed by 27 nations and promised to reduce the use of certain CFCs by 50% of their 1987 levels by the year 1997. Now, many amendments have such been made, and up to 196 nations have signed since that original 27 nations. Now, some of the more dangerous CFCs have been altogether discontinued, and scientists actually expect ozone levels to be normalized by 2050. So it slowly creep back to where they were before the use of CFCs. So it is not a disaster that will not fix. It's just it takes a while to get things back to where they were. So while the Montreal Protocol has been a success, CFCs are still very, very useful. And so many lower income nations argue they should be allowed to continue their use. Now, current technology is aimed to create CFCs that have similar properties while decreasing the inertness, which originally led to the ozone depletion. So we make them slightly less inert so they react. So, for example, HCFCs, hydrofluorochlorocarbons, and HFCs, hydrofluorocarbons, give the molecule some hydrogens that will be extracted by hydroxyl radicals, which then leads to further decomposition. So if we don't have these chlorine, if we have more reactive radical bonds, those will be lost first. And if the molecule degrades before it gets to the stratosphere, then we're avoiding the problem. So that's why the addition of these hydrogens in here. So while the reactivity does lead to reduced usefulness, it greatly reduces the ODP. So HCFC 22, ODP of 0.05, atmospheric lifetime of 12 years. 142B, 0.07, 17.9 years. 141B, 9.3 years, 0.12. 123, the 0.02 ODP. So you can see a lot lower lifetimes, and some of them are very low ODP. Now, however, these HFCs are more stable than the CF bond being unable to be broken easily. So thus we have a ODP of 0 HFCs in these HFCs versus the HCFCs. But it does give them a much longer lifetime. And these HFCs will contribute in other ways to environmental hazards, as they can absorb infrared radiation and thus generate the greenhouse effect, the greenhouse warming potential. So you look at the GWP, the greenhouse warming potential. So you look here like, oh, okay, some of these ODPs are very low, but you have a high greenhouse warming potential. So like 141B would actually, let's say 123 is probably the best, as a pretty low ODP and a pretty low GWP. But some of the ones with 0 ODP have a pretty high greenhouse warming potential. So HCFCs seem to be the better option. They have a low ODP, but they also have shorter lifetimes, and so they won't warm up the atmosphere as much. So you want something that doesn't hang around for very long when it gets put in there, and doesn't have other unintended consequences. There's also issues of bromine compounds. bromines, so you notice the CFCs did not have a bromine attached, but we talked about BRO being a possible radical. So bromines are even more reactive than chlorines, 60 times more reactive. So where are their sources? One of them is halons. Bromines containing one carbon or two carbon compounds. They're often used for fire extinguishing or in flame retardant fabrics. They work by smothering the fire with a high density gas. So you essentially form bromine gas that pushes out all the oxygen. And most burning reactions are radical based reactions. So when they're releasing an HX molecule, a hydrobromine molecule that can then trap high energy hydrogen and hydroxy radicals that are produced in this combustion. So HX can form hydrogen gas and a bromine radical, or HX can form water and the radical. Now the effectiveness of these halons, we have fluorine is the lowest, chlorine, and bromine, and iodine. Fluorine isn't easily released, and iodine is actually too weak. It starts forming radicals before the flame formation even occurs. So bromine is in that high useful state. So halons and methyl bromide usage is also to be reduced by Montreal Protocol. So real quick, we'll look at some math. The kinetics of catalytic ozone destruction. So we're going to like maybe another slide or so, and then we'll be done. But considering the destruction of ozone by NOx, the rate can be described by the following two equations. The rate of reaction 1 is equal to, it's a secondary type reaction where we have the rate is equal to its equation constant K, 2, the concentration of NO and the concentration of ozone. And then the second step is the rate 2,3 for the its constant, NO2, and monooxygen. Now the K itself can be determined by the Arrhenius equation that looks at a collision effect and the activation energy barrier. The activation energy barrier of the second equation is really low. Really, really low. Well, essentially 0. And so we get the rate constant A. So if we look at both the Ks are very small, but we're looking at molecules. So 3.5 times 10 to the negative 15 versus 9.3 times 10 to the negative 12 for the second step. So the second step is something like 3,000 times faster based on K. But looking at this, at 20 kilometers, which has a temperature of 220 Kelvin, the relative amounts of our concentrations is ozone is this many molecules, 3 times 10 to the 12th. NO is something like 2 times 10 to the 9th. You notice monooxygen is very low, 2 times 10 to the 7th in comparison to everything else. And thus the NO2 is 8 times 10 to the 9th. So the rate of the first step, plugging all of our numbers in and multiplying, you get something like 2.1 times 10 to the 7th molecules per centimeter cube per second. Even at the lower activation energy barrier, at those lower concentrations, the rate of the second step is 1.5 times 10 to the 6th molecules per second. So essentially, the first step is over 10 times faster. There's 10 times faster. That even though there's no activation energy for the second reaction and the K is faster, because our monooxygen concentration is so much slower, the second step is the rate determining step. Now, if a similar reaction is calculated at a higher altitude, the first step can become the rate determining step. Because even though the temperatures increase, and thus will increase the rate constant for the ozone depletion, the concentrations of ozone, NO, and NO2 become very similar. They drop. They're not significantly less, but the concentration of monooxygen will increase a bunch at this higher altitude. And because the increase of that, the second step will speed up. The concentration of monooxygen at 30 kilometers has increased to 2 times 10 to the 9th, which is increased by a factor of about 100. And this is, of course, due to more light, more high-intensity UV light that splits more dioxygen into monooxygen. And so we get the second step speeding up. Now, I'm going to stop there. Where we will look at when we get back, or Wednesday, one way or another, is some of these cycles, some of these reactions that don't actually contribute to ozone depletion. They do other things. But we'll have to look at that a little bit later. For now, that's where we'll stop.